Logic gates and Boolean expressions, part 1. We're going to be looking at Boolean variables, truth tables, logic gates, and De Morgan's laws in this presentation. What you have to know? Well, the two states of Boolean variables, truth tables, the standard logical operators or connectors called not, and, or, and, nor, exclusive or, and we might also look at exclusive nor, XNOR. Combining logic gates, De Morgan's laws, simplifying Boolean expressions, construction of logic gates. Where it all starts? Well, it all starts with the supply of electricity and the object, the item, making a decision is known as a gate. So here our gate is open, or it's a switch in other words, open being the binary 0, closed being binary 1, and if it's closed our lamp can light up. And that's as simple as it gets because we're dealing with electricity. So it can either be on or off. However, an electronic reaction relies on not just one input but often many inputs of voltage, and a decision needs to be made on this. High voltage 1, low voltage 0, or no voltage 0. The gate needs to be to make a yes-no type decision or Boolean based on several inputs. Logic statements can only be true or false because they run off electrical power. In search of the truth. A truth table is just simply saying what are your possible states, and every variable or input has two states. X is true, false, Y is true, false. Now when we combine these, they go beyond just their own state, but the combination varies according to the true and false table. So we actually end up with 4 rows. So what are all the conditions for each variable, true or false? But what are all the combinations and conditions for X and Y together? And we extend beyond that. Here they go. So when X is true, Y can be true, and Y can be false. Or Y can be false, and vice versa. So two variables means there are two conditions, but combining them means there are 2 to the power of 2 combinations. Okay? So we say when X is true, Y can be either true or false. And when X is false, Y can be either true or false. False equals 0, true equals 1. I think we know that by now. This is just taken straight out of the textbook, showing you that switch on a circuit. All possible combinations of inputs. Let's look at the OR connective. Now the OR connective, we say take any one. So in other words, take any switch that's on. This is the OR connective or OR operator in our truth table. We've got one supply on this circuit, but this circuit, you probably know the correct term, this circuit has 2, let's just say, paths or channels. There is a correct term, it escapes me for now. Here our supply is, we can have X closed or Y closed. So X is closed, and our lamp lights up. It does not have to be both. It doesn't have to be an and. Let's just have a look there. When X is open and Y is open, the lamp is off. So let's just do that. When X is open or Y is closed, it's on. If X is closed or Y is open, it's on. And if both are closed, it's on. So that's why we say take any one, or take any one that's closed, and it will be on. Look how many ons there are in this particular OR connective, OR function, switch arrangement, and truth table. Oh, yeah. Okay, and there's our full truth table with Q being the output. We have 3 possible situations where the output is turning the lamp on. And our little cheat sheet is take any one. 3 burgers. Take away any one. Right, our AND combination. Somebody says, hey, what's with the burgers? I hope you get it. Right, take only ones is my cheat sheet for the AND connective. Alright, what's the situation here? Well, our refrigerator, this looks like the freezer compartment, but anyway, our refrigerator has power coming into it. Okay, so that's one variable input. And the door being open. So that's actually closing the gate at that point. The combination of X, our plug, our supply, and Y, the door being open, means that the light comes on. So there's our truth table. And of course it's X dot Y representing X and Y. Our output is not on, and not on. It's only on here because we have to take only those that are on. Take only ones. What was our other cheat sheet? Do you remember? Take anyone, and it's on. This is take only all of those inputs with ones. That's what the cheat sheet means. Take only the ones that are on or 1 to get the 1. And what's our memory picture? A big fat burger. Right. Now we got variables P, Q, R. Okay, those are our inputs. We'll look at 3 variables. Step 1, list all conditions for each one. Step 2, we require 2 times 2 times 2. So 2 times 2 is 4, times 2 is 8 entries or rows in our truth table. Step 3, for every P, input P that's true, we have a Q that's either true or false, and for every Q that's true, we have an R that's either true or false. Okay, just remember that you need 2 choices for each variable. And this is the answer. Alright, so 8 rows. 1, 2, 3, 4, 5, 6, 7, 8. Those are our inputs at the top there. P and Q. There are some statements you can test against these variables. The first is AND. Sometimes it's represented by what's called a little cuppy, an upside down V. Just remember that. Haven't seen it in the exam, but if you're looking at notes, etc., you might see that. P and Q. The statement is only true if both P and Q are true. For AND, both have to be true. Testing it is the output of the P and Q variables. Okay, P or Q, let's try it. The statement output requires P and Q to both be false in order for the OR statement to be false. Otherwise, all the other statements are true. Take time to try it, pause, make sure you got it right, and test. Yes, we've been through that. Okay, let's try this now. A switch arrangement for a combination of AND OR gates. Do you remember we said you could get many inputs? So not just one input, there's many inputs coming. Here comes X, there's Y, and there's Z. But when it comes to this particular circuit, it can be Y or Z. And then we will get Q lighting up. So let's have a look at this one. What do you reckon Q equals? Okay, what do you reckon Q equals? Let's have a look. Well, Q is a result of X and Y, or X and Z.